Okay, so hi everybody, welcome to our weekly seminar here at the Institute of Astrophysics. Today we have the pleasure to have with us Klaas Wiersema. I hope I'm pronouncing it correctly.
Yeah, that's good.
I did my best. So briefly about Klaas, he did the PhD at the University of Amsterdam, and after which he moved to the UK, where he worked as a postdoc in three universities, if I'm correct, the University of Leicester, Warwick University, and the University of Lancaster. Then in 2023, he moved to the University of Hertfordshire as a senior lecturer. Class research focuses on the spectroscopic and polarization properties of transient sources. And in recent years, he also got interested in using big astronomical telescopes for space domain awareness. And this will be precisely the topic of today's talk. So thanks for being with us. The floor is yours.
Yeah, thank you very much. I will share my screen in my presentation, which means I probably won't be able to see any faces anymore, but just shout if you have a question or something else you'd like to ask or say. Hopefully you can all see my presentation slide here. Let me know if you don't. Right, so my name is Klaas Wiersema, and I'm at the University of Hertfordshire now. And the work that I'll be presenting to you is all very preliminary and very much in prep, but maybe that's extra fun. And this is work done in a collaboration with lots of people in the UK, as well as government partners like DSTL, which is the British Defence Science and Technology Laboratory, and the US Air Force and partners in other countries. So what I'll be talking about today is using astronomical polarimeters and astronomical instrumentation in the space domain awareness field, because it turns out that we astronomers have really good equipment. We can do some really nice measurements that commercial companies and government R&D labs often don't have. So my normal interests, my normal day job, if you like, the research side, is multi-wavelength observations of transients, of astronomical transients, particularly supernovae, gamma ray bursts, and those sort of things. And I build the instrumentation as well from time to time. But I got interested in using those skills in the space domain awareness field a few years ago, and that's been a lot of fun. So I've really come from this out of a position of curiosity, thinking what would it look like if I point a certain kind of instrument that we have in astronomy at a satellite? Well, what sort of signal would I get? And there's a lot of fun to be had in this field. Now, a lot of the stuff that I'll be presenting today is very much still in prep. A lot of it is data that I only got very recently. So don't expect too much quantitative stuff, but you'll be seeing a lot of nice data, hopefully. Okay, so just give you an introduction on space domain awareness. So space situational awareness or space domain awareness, people use either of those, is the art of keeping track of objects in orbit and predicting where they will be at any given time, how bright they will appear. So we usually have different regimes that we consider here, given by the orbits of the objects. So we have the low Earth orbit regime with orbits less than about 2,000 kilometers or so from the surface of the Earth. So those are satellites like Starlink, for example, but also astronomical satellites like the Hubble Space Telescope or SWIFT or so on. Then we have the geostationary orbits. So those are at very high altitude, at 35,000 kilometers or so. And of course, those are orbits where the orbital period is the same as the rotation period of the Earth, more or less. So they stay above one location of the Earth, which is very advantageous if you want to serve things like TV signals and so on. Then there are other orbits in between, as you can imagine, including some highly elliptical orbits where we also have some astronomy assets like XMM, the satellite. Now, slots in geostationary orbit are on the equator or at a specific inclination with respect to the equator. And there's only limited space there, as you can imagine, and there's only limited frequency access. So that is quite highly regulated through the ITU about who can transmit and who gets which slot in geostationary. Nevertheless, there's also a lot of room for maneuvering in there, which we see quite frequently these days. At low Earth orbit, things are a little bit more Wild West. There's much less regulation to which orbit is used by whom and why. There's some informal collaboration, but there's little enforced law, if you wish. So this makes it interesting to work out where objects are and how big they are. One of the reasons for that is the most extreme one is because of collision risk. So if you consider the circular velocities of high orbits, you can see they're pretty fast, which means that an object of just a gram orbiting at 400 kilometers and impacting a stationary object imparts an energy of nearly 90 kilojoules, which is a huge amount of energy. A collision with 10 centimeter piece of debris is often considered likely to fully destruct a satellite. Now, since satellites are very expensive, particularly GEO satellites in a geostationary orbit, this is a real concern. So even though the probabilities are relatively low, the associated cost is very high, which is a bit of an awkward situation to be in. But full destruction is not the only worry really for satellite operators. There's also a really important cost of taking evasive action. So if you know that another satellite or a piece of debris is coming in the way of your asset, you may want to move out of the way. That costs fuel, and launching fuel to high orbits is very expensive. So there's a cost associated with taking evasive action. If it's another active satellite that's approaching you, then who moves? Who takes that cost? Is it you or is it the other partner? And how do you decide that? There's not really much in terms of traffic laws currently out in space. So this is not easy to do. That makes it really important to very accurately monitor our near-Earth environment and know where objects are, how big they are, what their area of impact is, and whether they are tumbling or not, for example. So in the space domain awareness arena, we use different sensors to do these things. Obviously, there's optical telescopes that watch reflected sunlight of objects. That's the one we are all most familiar with, really. Then there are active radars. Those are generally limited to low Earth orbits because of the way that the flux drops off with distance. Then there are active illuminations using lasers. So you target objects with a laser and then you measure its return signal. And of course, there's radio frequency monitoring for active signals emitted by objects that you can use to get Doppler shifts, for example, and velocities. Now, normally all of those are used together to get a holistic picture of the orbits and the orbital behavior of objects. And this is a really big, high money field at the moment, space traffic management, because of the associated cost on objects and because of the large number of objects in space, which is illustrated with this plot. This is now a slightly old one. So you see horizontally the time in years and the number of objects in space vertically. The orange line shows you the payload. So these are active satellites. You see that steadily increasing for quite a long while until sudden uptick, which is caused by the launch of an assembly of mega constellations, particularly Starlink. Now, this number is now considerably higher. This was a graph from 2021. You see in green the number of debris objects that are known up to a certain size. And you see these very steep rises at a couple of places. I put some arrows there. Now, one of them is caused by the collision, accidental collision between two satellites in space, creating a cloud of debris which dissipates out, hits other objects from time to time, creating more debris. And there are also upticks caused by anti-satellite weapon tests that have been performed by two countries in particular, destroying satellites, creating large clouds of debris as well. Now, so there's a steep rise of the number of objects in space. That makes the topic of traffic management more important. One of the numbers you'll see a lot are things called conjunctions, which is when the probability of collision is larger than 10 to the minus 4, and the expected pass distance between two objects is less than a kilometer. And the pass will happen within the next 3 days. That's when a conjunction alert is issued. Now, in 2021, there were about 150 of those in a year. Currently, we're at a situation where there are hundreds per day. So this has dramatically increased in rate because of the launch of so many objects in low Earth orbit. Right. Now I'll show you this video. Hopefully that will work. Oops, it might not. I always forget how to do that. There we go. So this is a video taken with some optical telescopes of objects in geostationary orbit. And this is proximity operations. So these are objects coming very close to one another for a variety of reasons, and operating very, very close in each other's environment, which can be dangerous and can be useful at the same time. Now, this animation shows you cases of accidental explosion of objects in geostationary orbit. So these are far away from Earth where the debris rate is lower, but still collisions occasionally occur and satellites can explode, which is a real worry because they are so expensive. Now, proximity operations can be hostile, so they can be made by spy satellites. This is a very strongly growing field, and we see lots of spy satellites currently doing proximity operations to commercial civilian assets like TV satellites, which is a real worry. And there have been several hacking attempts from those close proximity satellites onto civilian satellites. So this is mainly done by Russian and Chinese missions, but there are also ones from the UK, for example. But there's also a civilian use of proximity operations, for example, in-orbit refueling, which we'll get to in a moment. So these things, both in terms of risk and in terms of actual explosive destruction, have an effect on the profit margin of satellite operators and insurance companies. So it's important to monitor even at geo orbits what is going on there. So several companies are contracted to provide data like this, usually exclusively to certain customers, particularly the military, but also to operators and so on. And that is quite exciting. There are also intergovernmental supply of data as well, of course. Right. Whoops. There we go. So in astronomy, we also are affected by this proliferation of objects in the near Earth environment, because some of them are very bright, so they affect our data, which we see very frequently, but typically at a rate now of about 10% or so of data that are, whether that's pixel acreage or actual frames, that are affected to some degree by satellite trails. And that has an effect on the cost of a scientific experiment, of course, which is not covered by the polluting party. Of course, in the radio, the situation is potentially worse. A lot of satellites are leaking into astronomical bands, some of them protected bands, but there's very little enforcement of those rules, really. Now, the things that affect us, our data, are things like the orbital height of a satellite. Lower Earth orbit means that they come over quicker and are only observable really at twilight, so they have less of an impact, but they are brighter, of course. Whereas objects that are further out take longer to cross your field of view, so they have a stronger effect, but they can be fainter. Orbital inclination, of course, makes a difference. If your telescopes are in the far north, you have much less of a problem than if you're on the equator. And how bright the object itself gets. That has to do with the material it's made of, the coatings, the shape, the size, and the orientation of the object with respect to you and the sun. And of course, there's the radio behavior of objects when they transmit real data or when they're malfunctioning as well. Now, as you know, many mecha constellations are currently in preparation and being launched at the moment. Like Starlink, there's about 9,000 Starlink satellites so far. OneWeb, Kuiper, Xinhuang, Xianfan, Blue Walker, there's many of these companies. OneWeb, of course. Oh, I've got one. So there are many objects being launched. Some of them in very low Earth orbit, some of them in somewhat higher ones. There are hundreds of thousands currently planned to be launched, and the realistic number that you see is perhaps close to 100,000 or so over the next decade. So to combat these problems, there is a working group from the IAU called the CPS, the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference. And I can recommend everybody who is interested in that aspect, in the sustainability aspect, to register for that as astronomer and contribute data. There's also the Gnosis network, which is an academics and industry knowledge exchange network that I'm very active in, which is mainly run in the UK, but has worldwide components as well. Okay, so why do I want to do polarimetry of satellites? What's the point? Well, as astronomers, we would quite like to know that if I point my telescope at a certain area in DEC, say of a high redshift galaxy or something like that, what is the chance that I will get a track of a satellite through it, and how bright will that thing be then? So I need to know what the position and direction is of these orbits going through it, what the brightness of an object will be. So is it going to affect my data, or do I not have to worry? What the colors of that object are going to be, and what its polarization is, because the polarization has an effect on the way the noise in the telescope propagates. We also need to know, so to do these things, we need to have very good orbital elements of objects. We need to know the size and the shape of an object in space. So we know how much reflection we can expect. What the orientation of the reflecting elements is. Is it going to glint, for example, which would be much worse than a constant signal? What are the material properties of the reflecting elements, or what are the refractive indices? And then, of course, what does our own atmosphere do? Now, some of those things are very nicely probed by polarimetry, which is why I was initially interested in doing these things. So from polarimetric information, we get a lot more than just from photometry, as the sort of jokey meme in the bottom illustrates. Now, to very quickly talk about polarization as well, very, very short, because I know many of you know very well what that is that polarimetry is the study of the preferential orientation of the electric field factor of the incoming electromagnetic waves. You can imagine that as holding a piece of paper out and tracing with a pencil the orientation of the electric field component of an incoming wave train, which may look then like an ellipse. Now, that ellipse may have a certain orientation with respect to your coordinate system. We call that a polarization angle. And the ellipse will have a certain ratio of semi-major and semi-minor axis, which we call the polarization degree, or the degree of linear polarization. Now, this is often expressed, these things, in something called the Stokes parameters. So there's a picture of Stokes on the right here, looking very glum. The Stokes parameters are really useful because they allow you to make quick calculations without having to worry too much about coordinate transformations all the time. And they allow you to apply matrix computations onto the Stokes vector rather than having to deal with all kinds of sines and cosines all the time. So this saves a huge amount of work, and Stokes was very happy having worked out the Stokes parameters, as you can see from this picture. This is him after using Stokes parameters to calculate things. Okay, so why do we get polarization anyway from reflected light of a satellite? Now, as we all know, or may remember from our physics undergrad, is that the process of specular reflection, so reflection like a mirror, induces linear polarization. So if you consider a wave that's reflecting off of a surface, then the electric components parallel and perpendicular to the plane of incidence have a different reflectance. So unpolarized light that gets reflected therefore becomes partially linearly polarized. So there's an example here on the right, which is reflection from air to water, I believe, using the Fresnel equations. So you can see the reflectance for the S and the P orientation of the waves. And you can see that the reflections differs. So therefore, at certain angles of reflection, you will get polarization because one of those components is more reflected than the other. Now, the maximum of this polarization is then near the Brewster angle. Now, the amount of linear polarization and the polarization angle that you detect then critically depend on the refractive indices of the reflecting material. So that's the property of the material that will give you the amount of polarization you expect at a given angle. And of course, the reflection angle comes in. So if you're reflecting off at an angle of 0, you expect no polarization, as the graph shows you. If the angle is, say, 50, then you expect quite a lot. And of course, it also depends on the polarization of the light before the reflection. Now, sunlight is generally unpolarized, so that's not really going to be an issue. But moonlight, for example, is somewhat polarized, and therefore you might get some enhancement of that through reflection. Now, when we observe a satellite from the ground, you don't get a nice clean mirror that's reflecting. There's all kinds of bits on a satellite that reflect, of course. And of course, reflection is not always so simple as specular reflection, which I show on the left here on this plot. Some of the surfaces of a satellite are quite rough, so you can have some rough surface reflection. There may be a combination of specular reflection with some subsurface scattering, if you have a layered material where some of the light comes through. Think, for example, about solar panels. And there may be a situation where you have rough surface reflection and subsurface scattering all contributing as well. So this makes satellites a little bit more complicated, but it turns out that the specular reflection approximation works really well for most of them. Now then we have to think a little bit about angles. So we looked here at this plot where the incidence angle tells you how much polarization you get combined with the refractive indices. The same thing's true in orbiting satellites. So as the angle changes, we should get differing amounts of polarization. And what we use for the angle to encode that, if you like, is the solar equatorial phase angle. So that is the angle defined as the longitudinal component, the angle between the satellite and the anti-solar point. So the phase angle is the angle between the sun, the observer, and the satellite, but we often use the anti-sun position to encode this. That means it is 0 when the sun is exactly behind you and the satellite right exactly in front of you, if that makes sense. Now this is usually quite a good description of the geometry of the problem, but if you have a satellite with all kinds of bits on it, it's a cube perhaps with some panels sticking out and some antennae and whatnot, then it's a little bit more complicated because it depends also on the position of that satellite with respect to that coordinate frame. So the roll and the pitch and the yaw start counting in that as well. But you'll see in the coming plots later that I'll be mainly doing things with solar phase angle. Now, in astronomy, we're sort of used to doing calculations like this because it's how we calibrate telescopes. So a lot of telescopes are fed through tertiary mirrors. Tertiary mirrors, because they have a reflection of 45 degrees and they're coated in aluminium, will impart polarization. And which we can model very nicely using a Mueller matrix chain. So it's a chain of matrix operators that operate on the Stokes vector that comes in to give you the Stokes vector that you should detect in your instrument. So you take a chain of all the optical elements that you encounter, or that light encounters, to make a total system matrix, if you like, to solve the system. And this is a way that we calibrate a lot of polarimeters in astronomy, but we can use the exact same approach on satellite reflections, so encoding them using a empirical system matrix that we can then later try to work out from the elements in that matrix what were the refractive indices. So here's some example of some of that calibration work on. This is a polarimeter on a telescope in Chile, and you can see quite nicely that we can fit observations of zero polarized objects quite nicely with one of those system matrices that we've fitted. So this works quite well. Now, in theory, we could do the same thing with the satellite and produce empirical system matrices of their behavior. Now, the instrument that I use a lot and I will be mainly talking about today is a MOBTOP on the Liverpool telescope. So there's a picture of the Liverpool telescope on the right here. It's a 2-meter telescope on the island of La Palma, where a lot of big telescopes are located in the Canaries. It's a 2-meter one and it's fully robotic. So all the observation decisions are made by a robotic scheduler at the telescope, and there are no humans in the loop, which is quite helpful for a lot of these observations. So it's a robotic telescope in La Palma. It's 2 meters, so it's sensitive also to some fainter objects, which is very helpful. It's robotic, which makes it nice for scheduling in short observations. You're not disturbing somebody's observing night, basically. And it is quite capable in doing some non-sidereal observations, so where the tracking of the object is not along the sidereal period. Now, the instrument I use is called MOBTOP, which is an imaging polarimeter. Its schematic is there on the bottom left. It uses a continually rotating wave plate, half-wave plate, for linear polarimetry, which is connected, if you like, to 2 detectors, which are CMOS detectors, that read out simultaneously as the wave plate rotates at every 22.5 degree turns. Now the wave plate keeps on rotating. It's got 2 speeds. It's got an 80-second speed, so it takes 80 seconds to do one full 360 turn, or 8 seconds, which is the fast mode. So you have a slow mode and a fast mode. And of course you can stack them as you see fit. Right, so they record an image every 22.5 degrees. You need 4 of those to get a QU measurement. So you get 4 measurements per 360-degree rotation of the wave plate. So in other words, the cadence that we get from this is 20 seconds in slow mode or 2 seconds in fast mode. So a polarization measurement every 2 seconds is very useful for satellite work. There's a picture of the instrument. It's not the most good-looking instrument in the world, but it works. Now, how do we observe these things? This may be a bit boring for many of you, but for the keenies, I'll explain that a bit. Is that unfortunately the TCS of the Liverpool telescope can't handle two-line elements, orbital elements directly. So I download fresh two-line elements from providers, particularly SpaceTrack, which is the US Air Force one, or SatixTrack. Then generate from that ephemeris, then ephemeris rates. Upload those to the GUI of the LT, where I define an observing time with a certain slack. So it allows a window of observation to be found to do your observation in. And then the TCS of the telescope will interpolate over the ephemeris table linearly to track the position of an object. Now, that works reasonably well if you have fresh TLEs. And that's the problem sometimes, is that our field of view is only 6 or so arc minutes. So you need orbital elements of your satellites that are newer than about 2 days. If they get older than that, you start mispointing quite frequently. Okay, so now in this work that I will present later, you'll see that there are a lot of light curves. So those are obtained at the same time with telescopes operated by the University of Warwick, which is about 250 meters away from the LT. So they're really on the same side, so there's no parallax effects to worry about. They provide very high cadence photometry of these objects that we can combine with the polarimetry. Now, Liverpool telescope is a 2-meter telescope, and it was built quite a long time ago now, which means that it can't track very fast. So the fastest rate it can do is about 100 arcseconds per second, and I wouldn't even advise using that. So low Earth orbit objects are just not possible. They go way too fast over the sky, so we can't track on those. But geostationary objects, which go at about 15 arcseconds per second, they are really quite suitable. So they work quite well. Now, of course, as you take observations, this is one of the exposures from MobTop. I just picked a random one. There's a satellite there circled. It means that all the stars are trailed because we're tracking on the satellite. Now, that can be a bit annoying because sometimes those star trails may go over your object and then artificially bump the flux, and then you get wrong measurements. That's unfortunately something we have to live with. So here you go. You can see the stars moving over the frame where the satellite stays in the same place. Okay, now, so the data analysis, I won't go into too much detail because it's a little bit boring, and you can read about it in the paper from 2022. So what we effectively do is have a script that takes data, extracts the information from it that it needs, calculates the solar equatorial phase angle for all the observations, calculates the normalized flux ratios of the ordinary and extraordinary ordinary beam, of the observations, and then computes from that the Stokes parameters through a Fourier analysis. Then we correct for instrumental polarization, which is quite significant for MobTop because it's fed by a pick-off mirror, by a tertiary mirror. So we correct for that, and then we correct the depolarization as well, which is also quite significant for MobTop. And then finally, you have to correct for the fact that the instrument is rotated with respect to the sky at specific values because it's on a factory and Naismith platform. So we need to correct for that as well. But that's how the system, the data analysis works. It's fairly standard, really. So what I hope to show you now is some examples of fun stuff we see when we point polarimeters on a big telescope at satellites. So I picked 4 projects that I'm currently running that I think are quite fun. So I only picked them because I was curious about them and I think they're fun. But it turns out that a lot of space companies are very keen on this stuff. So that's quite nice. Now, I'm going to show you examples of LT and MobTop data of geostationary objects for the reasons that I showed you earlier, is we can't track LEO, it moves too fast. That's the only reason. I'm currently building new observatories and instruments to tackle that range of objects as well. So we'll look a little bit at active geostationary satellites and their behavior. We'll look at proximity operations, in particular the docking of MEV2 with one of the satellites. We'll look a bit at the Yorp effect in the graveyard of geostationary orbits, and at a really funky thing to do with satellites to look at what the expected radiative transfer behavior is of exoplanets. Now this, oh yeah, I should say this is all in prep and none of it's actually finished, and there's a lot of preliminary stuff in there, but hopefully it will be interesting. Now, I told you earlier that we got supplementary high cadence photometry that comes from this set of telescopes here. This is on La Palma, so you may have seen it if you've been to La Palma before to observe. This is the Warwick platform. You see a 1 meter telescope at the top, and then there's a large set of other telescopes of smaller sizes, which are dedicated to space domain awareness. So they are 40 centimeter and 30 centimeter telescopes. They co-point, so they can provide us simultaneous high cadence data in a range of wavelengths, ranging from the J and H band in the near infrared to the U band in the optical. So we generally take 4 optical bands simultaneously, but the readouts are slave to each other, so they're taken at exactly the same time, simultaneously with the LT plus 1 infrared band. So we get colors at the time scales of about 2 or 3 seconds, which is quite attractive. So what do active satellites look like when you look at the polarization? Now, we saw earlier from the reflection from at water in that particular case, but from the standard Fresnel behavior, that you expect at zero angle, zero incidence angle, so in other words, zero phase angle, that the polarization should be 0 for specular reflection. And then at higher angles, the polarization should increase and come at the maximum at the Brewster angle or near the Brewster angle. Now, this is a set of observations that was published in 2022 by another group using the Nordic Optical Telescope. You can see in green, red, and blue linear polarization of a couple of active geostationary satellites and a TDRA satellite. It's a slightly lower orbit, and you can see that this behavior is quite is observed as well. So at zero phase angle, the polarization is low. At higher phase angles, it increases, but it doesn't increase linearly. It has a somewhat complex shape, which is caused by the materials and also the orientation of the reflective elements with respect to you as the observer. Now we can, of course, get much higher quality data with MOPTOP, in particular higher cadence. So this cadence here, as you can see, is maybe a few minutes, but with MOPTOP we can do seconds. So this is a MOPTOP observation, set of observations of an active geostationary satellite called 4.6, which is a TV satellite that broadcasts soap operas to the Scandinavian countries. So if you're in Norway and Sweden or Finland, this is a satellite you may well have been tuned into to watch soap operas. So this is at a timescale of 2 seconds. So this 2 second timescale. There's about 2,500 measurements in total in here. You can see the signal to noise varies because sometimes clouds come over. But you can see a slightly more complex behavior than we saw before. So we still see that at zero phase angle, the polarization is very low. Of course, when the polarization is low, then the polarization angle becomes unconstrained. So that's why it gives you those erratic data points in polarization angle, because the polarization is very low. Because the error in the polarization angle scales as the error in the polarization over 2 times the polarization value. Now you see also a change in polarization angle very clearly when you cross over the zero phase angle regime, which is what is expected from Fresnel specular reflection. And you can see that, although it's not so clear on this particular plot, is that there's a lot more happening that we didn't see before in the behavior. The lie curve of this satellite is plotted in the bottom panel for one of the observing nights. We can see a couple of things in there. So there's a maximum at 0. That's sort of expected. It means that there's some elements that are pointing directly at the sun, basically, that therefore reflect very well. You also see these sort of symmetric humps at minus 25 or so degrees and plus 25 or so degrees. Those are offsets from the solar panels. So the solar panels don't point exactly at the sun, but at a slight angle. That is done to manage the power intake over the year. So they produce maxima in the light curve there, and they also have polarimetric effects, which we'll look at in a moment. Then in the light curve, you can see on the right-hand side this period of intense glinting, where the brightness increases by 4 magnitudes or so over very short time scales, and we don't know what's causing that very well. So if you zoom in on a part of that polarimetric data set and light curve, you can here see the behavior at high phase angles. You see there's all kinds of stuff happening in light curve space, which is not visible in polarization space at all, which tells you something about the approximate size of the glinting object, because in the polarization we see the whole object averaged together, whereas the glints are dominated by very small facets in this case, so at the size of a few centimeters. You also see the steep decrease at the high polarization angles. We've passed there the Brewster angle, and we're now seeing a different element of the satellite reflecting, potentially a side panel or one of the antenna reflectors. At very small negative angles here, we're now near that place where the first hump of the solar panel was at -28, something like that. We see clear behavior of the polarization angle around that time as well, which we can model. Of course, we also took colors. This plot should have been easier to read. Unfortunately, it's not so well. So it's difficult to tell the difference between the V-band and the R-band data points. But we took sequential V and R-band observations in fast mode. You can see that there's a very clear wavelength dependence on the polarization, which is exactly what you expect from Fresnel behavior. So this is not unexpected at all. And we can use that to throw into our Mueller matrix codes to determine the properties of the reflecting object. Now, sometimes you can get lucky and you can get 2 satellites in the same field of view, even though the satellite field of view is very small for MOPTOP, 6 arc minutes. You can get 2 sometimes. So here we got 4.5 and 4.6 in the same field. So I got pictures of 4.5 and 4.6 at the on the left. So they look very similar. They both got a big antenna, phased array antenna, and they've got big solar panels. Now, to explain a bit what big means here, that the wingspan of these satellites is about 25 meters, so the size of a swimming pool. So they're huge. They're really, really big things. Satellites like this cost hundreds of millions of dollars. And on the right, you see the polarization behavior there over a very small range in angle, of course. So it's over 800 seconds. And you can see there that they are different. So these objects are very close in location on the sky, but they have quite markedly different polarization properties, which is caused by the fact that they have slightly different orientation with respect to the Earth to serve their customers. So we can derive that directly from our data. Right, I wanted to show you a little bit more about the glinting behavior of 4.6 because it is so interesting and so unusual. So as we saw here in the light curve, this is the same light curve I showed you earlier, I believe. You can see this period of intense glinting, and I've got a box drawn around an area that I zoom in, and that's a time range at which we took polarimetry data to see if the glinting here has an effect on the observed total polarization. So this is a light curve that came from one of the Warwick telescopes at a time scale, I think, of 5 seconds here. So this is the polarization that we see at the same time in fast mode, so again with 2-second time resolution. You can see in polarization space it does very little. It's a very clear gradual rise. There's a couple of deviating data points which may point to some behavior in the reflection properties. The polarization angle is almost entirely constant over this range. So it's interesting to see that the behavior that we see in the glinting light curves looks very different from the polarization. So from that, we concluded that this glinting is probably caused by the insulation blanket around the satellite, and that it's quite crinkly in this satellite. In some other satellites that we observed in this way, we saw that the blankets were much more taut, and you don't see this extreme glinting behavior. So very small differences in how the satellite was built can make a big difference in the observed properties. Right, let's see. Oh yes, I wanted to show you this one because this is about 2 weeks of light curves from 4.6, full night light curves obtained at 5-second time resolution. On the right hand end of things, so from about 30 degrees to 80 degrees in phase angle, is this glinting behavior. Each light curve is offset from the other one, so you can see the time behavior. You can see some features of there stay constant in phase angle, and some of them traverse with phase angle. So we can model that to see which features are responsible for these things. There will be a paper on this coming out soon. What you can also see in the top light curve there is a big dip. That comes from the fact that the Earth casts a shadow in space, and sometimes these geostationary satellites cut through the shadow and get briefly occulted by or eclipsed rather by the Earth. We can use that later, and in a couple of slides I'll show you some really cool results of that. Now, because we're co-pointing with many telescopes, we get colors. So at the top is the B minus R color of this light curve that I plot at the bottom. And you can see how the color of the received emission changes. So you see very strong color changes at certain parts of the light curve, and whereas in other parts of the light curve it's much more constant. And we can model this through codes doing bidirectional reflection monitoring and stuff like that. Now we observed the same source a year later, exactly a year later, to the minute, to see how do things change. So the satellite's active, it keeps serving its customers in Norway, so you don't expect there to be a major difference in the orientation of the satellite, though we don't know this for sure. So we can see how things change with respect to the year before from space weathering, for example. So that's the bombardment of energetic particles from the sun changes the upper layer of elements in space a little, including their reflection properties. So elements may become slightly redder or slightly bluer. So here I overlaid those two light curves on top of each other, 2021 and 2022. As you can see in the bulk behavior at relatively low phase angles, it's identical. There's no observable change. Whereas in the glinting part, there is change quite significantly. So we believe that this is caused by a very slight change in the orientation of the satellite, its housekeeping if you wish, creating a big difference because it just depends on which facets of the crinkly layer you're observing. In polarization, these are two polarization observations separated by exactly a year. We see that they are completely consistent with one another within errors. So in red, you can see with 21 observations, in blue, the 2022, and they are pretty much the same within the calibration uncertainty, which is quite interesting and very helpful. It also means that by doing this over a longer time scale, we can monitor changes in the upper layers of reflectors really well. I wanted to give you an example of proximity operations. This is the docking of the Mission Extension Vehicle 2 to Intelsat 1002, which was an active geostationary satellite, well, still is, which was running out of fuel. Therefore, because these things are cost $400 million, it's worth refueling them. But that's hard because it's all the way out in geostationary orbit. So Northrop Grumman built this refueling vehicle, which was launched and autonomously made its way to Intelsat 1002 whilst the satellite was operating. It never stopped serving its customers, basically, throughout this whole thing. Then it autonomously, more or less, went around its target, docked with the backside, and took over its fuel duties. So on the right-hand side, you can see a picture of Intelsat 1002 taken by the Mission Extension Vehicle with the Earth in the background, which is quite a spectacular image. I've never seen anything like it. This is all very exciting. So I observed this source in polarization space to see, can we tell the difference between the situation before and the docked situation after? And can we tell that MEV2 is a different object from Intelsat 1002? And it turns out we can. So this is some of the data. You can see the two objects apart with the red and green arrows, and docked with the blue arrow on the right. So if you look at the polarization, Intelsat 1002, when this is before docking, is at the top, and it behaves just like 4.6. So it's a very similar behavior, zero polarization at zero angles. It looks very normal. But MEV2 is at the bottom panel, and that looks rather different. So it's got much higher polarization at low phase angles, caused by the fact that it was maneuvering. It was trying to get around its customer satellite to dock with it. So it's a very different behavior, which we can easily tell apart in polarization space. This is some zoom in of some of the data, just a few hundred seconds, showing you the difference in behavior between Intelsat 1002 in red data points and MEV2 in blue. So they behave very differently. They're very easily separable in polarization data, which is not so easy to do with light curves alone. Now I wanted to move on to a different topic. This is YORP. So YORP is the effect that people see with asteroids, where if you illuminate an asteroid with sunlight, it will absorb some sunlight and re-radiate it as thermal emission. But if the surface of the satellite doesn't have the same albedo throughout, and the object is not spherical, it will get a torque, a very small torque, because of this process. That's called the YORP effect. So it expects satellites to, asteroids to slowly spin up over time. Now this is a very slow effect in asteroids. It can take years to measure this accurately, but it has been measured for a handful of satellites, a handful of asteroids. Now satellites in geostationary orbit are much lower weight, so they have a lower moment of inertia. They are really big because they've got these massive solar panels, and they are much closer to the sun than most asteroids are. So this makes them much more sensitive to YORP effects, basically, than asteroids are. Now, of course, you do have to worry about things like eddy currents, about residual atmosphere at 37,000 kilometers, magnetic field connection, and those things, and potentially things like inhomogeneities in the Earth's gravitational field and so on. But at geostationary orbit, those effects are very small. And it turns out that the YORP effect is likely a big contributor to the spin up and spin down of debris objects, so objects that are no longer actively controlled in the geostationary graveyard. So to test that theory, we did a survey of large objects in the graveyard. So these are no longer actively controlled. The only effects acting upon them are astrophysical. And we measured their spin periods and their orientation using polarimetry and using high cadence photometry. So an example is at the top left. That's Intelsat 507, that satellite, a big one. You can see the light curve in orange at the bottom, which shows a couple of peaks, showing you that it's rotating. Now, if you have a low quality optical data set of these things, it's very difficult to separate the real period from any beats that you might see. That can be very hard. In polarization, though, it's really easy to tell. So you can see the polarization light curve at the top, and these extremely well-defined peaks that you can see there with a period of 400 seconds or so. So this object is spinning really fast. This is a 30-meter object, right? Spinning every 400 seconds. It's pretty quick. And you see the polarization values are huge. 50% polarization is higher than you get from almost any optical astrophysical object, right? So it's very exciting stuff. We also see some very clear polarization angle changes rather over the spin. Now another example is on the right, which is a much faster rotating object. This is Express AM33, another dead object in the geostationary belt. You can see at the bottom panel the light curves from the Warwick telescopes in different bands. So we have colors as well, with a time resolution of about a second, because we observed over multiple periods that we can combine. And the polarization degree at the top panel and the polarization angle at the middle one. So combining these things together, we can really model what the spin axis of this object is. Is it spinning over its principal axis or not? And if so, how does its spin period change over time? So we observe these sources over a year, doing about 5 or 6 observations, checking whether their spin period is changing or not. Now, many objects tumble rather than spin, so they don't just rotate over one principal axis, they do over all three. And they transfer energy, if you like, between the spin of one axis towards the other one, and so on, like a joint up pendulum. So this is very complicated systems, but we see very clear spin up and spin down in all our objects polarimetrically, so which is quite exciting, really. Now, the combination of the photometry with the polarimetry will allow us to really solve these systems, if you wish, which is very exciting, but it's a work very much still in progress. Now, then I want to go to the last topic, which is the lunar eclipse bit. So this is a little bit of an in-between, but you'll see the relevance in a moment. So if you try to remember seeing a total lunar eclipse, I'm sure all of you will have seen them once. If you haven't, you really should, because it's a beautiful spectacle of nature. So in a total lunar eclipse, the Earth, the moon rather, traverses through the Earth's shadow. We get an umbra and a penumbra as the full shadow, if you like, and the half shadow from this process, shown at the top in the diagram. Now, during the traversal through the umbra, in that geometric situation, some of the light that comes from the sun is refracted by the Earth's atmosphere. So that means that in the middle of the umbra, the moon should be at the darkest, because it's very high angles and that's very unlikely to get that scattering. When you get near the edges, that scattering is much more likely. So you should see a soft edge on the Earth's umbra because the Earth has an atmosphere. Now you see that a little bit in the picture below. You can see the soft edge of the Earth's umbra, and it is darker in the middle. Now the full moon has a magnitude of about -12.5 in the optical, right? And the fully eclipsed moon is around 0 or so, maybe 1, something like that. So we drop in brightness about 13 or so magnitudes, which is a big difference. Right? This is what is it? It's a large amount. So the what we know is that the fully eclipsed moon is polarized. And we know that by observing it. So I observed it with MOPTOP, with the LT, a recent total lunar eclipse to measure its polarization properties over the moon's surface. So even though it's at 0 degrees phase angle, the polarization is still not 0, which is quite exciting. And we believe that this is caused by double scattering in the Earth's atmosphere. So as light traverses through the Earth's atmosphere and gets scattered twice, it becomes linearly polarized, reflects off of the moon, and then back to us. So we think we're seeing double scattering in the Earth's atmosphere. Now, as the Earth's atmosphere changes because of volcanic eruptions, or cloud coverage, and so on, the polarization of subsequent lunar eclipses should be different, and we indeed see that. So the polarization of lunar eclipses is very strongly wavelength dependent and changes from eclipse to eclipse. But you can also invert this whole scenario and say, if I observe the polarization of the moon, can I reconstruct what the state of the upper Earth's atmosphere was? So what are the scattering properties at, say, 12 or 20 kilometers altitude or so? And that's, of course, an interesting problem because we have the same scenario in transiting exosolar planets. So in transiting exosolar planets, the emission that we receive travels through the atmosphere of the planet to us. So the polarization that we expect to see from transiting exosolar planets is really dominated by the effect of this double scattering in the atmosphere of the exoplanet, which we don't know very little about. So what we would really like to know is understand the Earth sun system and moon system better to make an empirical model on what we might expect from exoplanets. Unfortunately, lunar eclipses are quite rare. So at any given location on the Earth, you see, so at any given observatory, where you may have your telescope or your polarimeter, you see a total lunar eclipse every sort of 7 years or so. That is fully observable, well above sort of M-2 and so on. Now, if you combine multiple telescopes over the Earth, you may see one every 2 years or so, maybe a year. So that is a very bad timescale compared to the timescale of changes in the upper atmosphere of the Earth, where cloud behavior and volcanic behavior has timescales of a few days or so, maybe months. So we can't probe that, and that's what we need to understand exoplanets better. So my idea there is to use active geostationary satellites, so they keep their orientation with respect to the Earth at all times, and observe them as they enter into the shadow of the Earth. In that process, if this double scattering takes place, we should see a change of polarization as it dives deeper into the umbra, and same with the egress when it comes back out. But you already saw before that with the full moon, that we lose about 13 magnitudes. Now, a geostationary satellite at 0 phase angle is typically something like magnitude 9 or so. So if you add 13 to that, it's makes you 23. That's way too faint for LT polarimetry. But we can capture the beginning phases of ingress and egress to see if we can indeed detect double scattering in the Earth's atmosphere. And more importantly, by observing the same satellite go in and out of the Earth's shadow at various days in a row, we can see if there's a change over time given by the orientation of the Earth and the cloud coverage and volcanic dust behavior. So that's what we did. Now we need geosatellites because LEO satellites dive into the shadow all the time, but it's always at low air mass, which is or high air mass. Sorry, that's a pain, and they do it so fast that you need a time resolution of better than a second to really understand that behavior, and we don't have that. At GEO, though, they take a few minutes to enter into the shadow fully, which is enough to really resolve its behavior as a function of time. So I observed a set of objects, I think about 10, multiple times over a period of about 2 months, no, 6 weeks, I think, around the equinox, which is when the eclipses happen, to see whether we see a polarization caused by ingress and egress of the shadow. Now, the nice thing is that we do. So this is data that I only reduced last week in anticipation of this talk. And we see an example of a satellite called Astra 1M. It's an active satellite, which is ingressing into the Earth's shadow and egressing on the right-hand side. So at the bottom, you see instrumental magnitudes of the brightness. So you can see it starts off flat and then deeply dives down in a way that is not linear. That is expected from the scale height behavior of the Earth's atmosphere and scattering that comes in. And we see at the top panel there on the left-hand side, the polarization. And you see the polarization is low because we're approaching 0 degrees phase angle, so it should be very low. And then suddenly it shoots up. Now, the same is true on the egress. So the egress is on the right-hand side, so it comes out of the Earth's shadow. At the bottom, you can again see the light curve. And the polarization, as I said, the top panel there, it starts off high, very quickly drops, and then retains goes back to its original behavior, standard behavior of slowly increasing polarization as you go to higher and higher phase angles. So indeed, there seems to be a strong effect of scattering in the Earth's atmosphere on the polarization properties of satellites at ingress and egress, which sort of helps us in this quest. Now, I won't talk about the outlier data points that I've circled there. They're all caused by an instrumental problem in the telescope to do with mirror flop. This is a bit annoying, but we could deal with that. Now, these are observations done in B band, where the effect of Rayleigh scattering, of course, is highest because the sky is blue. We also took observations in R band, where we see a very much smaller polarization increase as expected from double scattering. Now here's a situation where we had 2 satellites in the same field of view. You can see it on the right field of view. This is a random image. At the top is Astra 1M, and at the bottom is Astra 1P, I think, but I'm not 100% sure which object this is. And if I look at their behavior on the left, that's the polarization versus the magnitude. You can see that Astra 1M reaches the shadow quicker because it's further in the right direction, if you like, by about a minute or so, a bit less. And the polarization behavior is very similar. So they both rapidly increase as they enter into the shadow of the Earth. Right, now I'm going to wrap up here because I'm sure I'm running out of time. Work that we're still currently working on with a PhD student in Warwick and staff members all around is we want to combine a simple BDRM model, reflection model of the light curve, colors, and polarization all together to see can we reproduce the standard behavior that we're observing? Can we define an empirical Mueller matrix chain with minimal ground truth? Because often we don't have that. We're trying at the moment to do simultaneous multi-site polarimetry of the same object at the same time so that we can get different viewing angles and solve degeneracies in our matrix modeling. We are working on circular polarimetry, which should also occur for these sources because of scattering of polarized light. And of course, we'd like to get data at LEO objects, so we need some new kit for that. On the instrumentation side, I'm working on a sensitive wide field high-speed polarimetry machine specifically for SDA. A grant proposal was submitted, and I'm hopefully hearing the outcome this week. And then we're working on fast robotic polarimeters on 4-meter class telescopes, particularly the NRT, to extend this to fainter magnitudes, which would be very nice. And then, of course, there are extensions planned for MobTop. Now, I think that's all I have to say for now, and welcome any questions.
Thank you very much. Thanks, Klaas, for the very clear and thorough talk.
Sorry.
So I see some hands clapping. We are a bit past the time, but we can take one question. So please unmute yourself if you have any question. Yanis, I see you are unmuting you unmuted yourself, but we cannot hear you.
Can you hear me now?
Yeah.
Yes.
Yeah. Okay. That fixed it. No. I'm waiting for other people to ask questions. I have a couple, but I can wait.
Why don't you start with one meanwhile people thinking?
Okay. So one of, I mean, really cool stuff and interesting, and we've been trying to get into the business of satellite tracking in the Skinnegans Observatory as well, but we didn't even think about polarimetry of any sort. So one question I had was actually about the exoplanet polarization. Do we have an idea what kind of signal you would expect from
we
the
do,
scattering?
and of course it's very small. So
Okay.
so it comes out to sort of 1 part in sort of 10 to the 8, I think, something like that. So that requires a huge number of photons to do that with a real exoplanet, and an extremely accurate polarimeter. So those things, that combination doesn't currently exist. But that's also partly one of the reasons why it doesn't exist, is because the science, the case for it, so whether this signal should exist in the first place, was not sort of evident really. So it came from some me-scattering models and things like that, which are look quite believable, but having empirical evidence that this takes place and that can be calibrated against is very helpful. So there have been some attempts to calibrate part of this using Jupiter, for example, Jupiter limb data. That's in emission though, and it probes different scale heights. So it's helpful for things like comparing to hot Jupiters and so on, where you expect most of the signal, a good signal to occur in transit. But they're potentially not directly comparable to transmission measurements that we get from lunar eclipses and satellites like this. So it's a combination of it being super hard to detect, but would be really useful to detect it, and firming up the case that this signal is detectable in the first place.
Yanis, you can go with your second question if you want. I don't see any other.
Second is more technical. Did I understand correctly it was sort of in the beginning of your talk that you guys figured out how to correct the Nasmyth polarization?
Yeah. It turns out to be quite easily modelable. Yeah, so we've done this for
Really?
yeah, it's not that
Okay.
bad. Yeah, so what we do is we model the behavior of a aluminium coating on a glass mirror using observations of. So we did this for EFOSC2 and SOFI on the NTT at ESO, which are both fed by Naismith Pickoff mirrors, so by M3 mirrors. By observing zero polarization standards and polarized standards over a wide range of parallactic angle, and then you can fit analytical models to the behavior. And we got typical sort of accuracy of about 0.1%. You can't get much better than that using this model because there's too many second order effects that then come in. So for high accuracy, it's tricky, but for a 1/10%, this is quite easily doable. So we showed that our model, it's all published a couple of years ago. So we showed that our model is stable for a given configuration over several years. But of course, every time a mirror is cleaned or resurfaced, it needs to be recalibrated, but only requires 3 or 4 standard star observations to bring that onto the calibration. So our code is also public. It's all published on GitHub. And everybody's welcome to use it.
So actually, I'm working with some people on testing a new sort of prototype polarimeter for Colibri, which is a sort of a new telescope in Mexico that's supposed to be following up SVOM alerts, and they're facing this problem, and we've been trying to find the solution. So if you could send me those publications, please.
Yeah, certainly. Yeah, no problem at all.
Thank you.
Our code is fully public and can be used by anybody to convert. There's a similar code, it's all in Python. There's a similar code for that we used for calibrating the Naismith-fed polarimeter on the TNG, which was called Jano, I think, or Paulo, can't remember anymore. Which we use the same code for, and it also got very good results. Of course, you get better accuracy if you can also measure the crosstalk properly. So if you have a way of measuring for calibration, the circular polarization, but I know for many instruments that's not really possible. So that gives you a threshold really in accuracy of around 1/10% or so. Now these models are also used to model things like the instrumental polarization properties of big segmented telescopes like the GMT or the TMT in the future.
Okay, I don't see any other ups hands, so thank you very much again.
Yeah, you're very welcome.
We can stop here.